How's that? Is it visible?
Looks great.
All right.
Derek is going to provide the final talk of the session about a really cool functionality that's being added to ArcSat, a fiber feed spectrograph.
All right, thank you. So yes, you've stolen my thunder there. So I'm going to talk a little bit about a spectrograph that we are trying to commission in time of COVID on the ArcSat 0.5 meter, which is probably more familiar to most of you than it has been to me, and in the picture here. So the idea is to take this commercial fiber-fed shell spectrograph. It's this e-shell made by Shelyak, which is a French company. Their primary market has been advanced amateurs, but some institutions have used it as well. And to put this fiber-fed spectrograph on the 0.5 meter. So the idea is to provide a new facility instrument for moderate resolution. And of course, as we've already heard this afternoon, moderate resolution means different things to different people. In this case, it's about 10,000. So in support of bright star studies, synoptic studies, student research, and whatever else you all can think of to do with a spectrograph on this telescope. So I'm going to kind of do a show and tell to start with and kind of illustrate what we've got. So this is the actual spectrograph, the little black box here. And let me go through some of the parameters. It's a cross-dispersed shell with a prism cross-disperser, f5 collimator, R2 grading, f1.8 objective, and a 50 micron object fiber. This is shockingly similar to the spectrograph that I did my PhD dissertation with N years ago, where N is starting to get to be a very large number. The fiber is a little smaller, but that's about it. Resolution is 10,000 nominally. I would say we're getting a little bit better than that. And the wavelength range is nominally 400 to 700 nanometers. Going to 770 is fairly straightforward. I'd like to go a little short of 400 to get better coverage around calcium H and K. We are seeing H and K at the moment, but they're at the very edge of our wavelength range. And so one of the things I'd like to improve on is to go a little bit shorter. The light is there. It's more a software issue, which I'll get to in a few. So we have a science camera here, which is a TEC cooled device. It's an ATIC. Both of our cameras are. Sony CCD, about a 6 megapixel camera. The pixels are quite small, 4.54 microns. We typically bin 2 by 2. We're still oversampled significantly. It's a full 16-bit camera. Read noise about 5 electrons. Full well about 18,000 electrons. And the idea was basically to do this as off the shelf as we could possibly do it. All right, so we have controllers and calibration lamps also on the table here. It's this pretty standard mix, thorium argon, quartz flat field lamp, and LEDs to help fill in some of the missing wavelength coverage with the flat field. We have on the telescope itself, a second camera, an acquisition camera. This is another ATIC, somewhat larger pixels, roughly 1 minute. 1 arc minute field of view, which seems to work okay with the pointing characteristics of the telescope, but occasionally is a little bit challenging. Again, the other camera parameters are very similar to what we had on the science camera itself. Both of them are TEC cooled. They typically run 25 or 30 degrees below ambient, which in the middle of summer can be a little bit of a challenge. We also have the guide camera, which is the same as the guide camera that's always been on that telescope, the externally mounted camera. And then we have the fiber pickup. The fiber itself is, or the fiber pickup itself is an F6 input module, the 50 micron object fiber I talked about before, and 200 micron cal fiber. And then the guide camera itself sits on the telescope. Or on the guide telescope, and is about an arc-second per pixel unbinned. Certainly a large enough field of view to find things. The challenge comes more with the fiber input module itself in terms of finding objects. We haven't generally had problems, but it is one of the more one of the constraints we worry about more. If you're an ArcSat user, the interface should be quite familiar. It's remotely operable, VNC and Maxim to control the cameras, a Chrome interface to control the lamps. That all at this point works really well, and definitely kudos to Bill for getting this all to work so nicely. He's trying to make it better, but it is perfectly functional now. And if I can use it, I'm sure anyone else can as well. Just showing pictures, right? So this is what images look like from the Eshella, flat in the center, Alpha Lyrae in the on the upper left, and the Thorium Argon. So you kind of get a sense of what we see. Typically, we go from cover about 30 orders, 28 orders. The reduction software we've been using, so this is interesting because of course Adam and Jim are both working on projects which I'm very interested in, because it would be nice to be able to use what they're working on for this spectrograph as well, which I think would be a big strength for us as an institution in terms of not having to force people to learn many different software tools. But right now we're using Windows-based reduction software, which Shelyak is manufacturing. It is in beta release. It has not been widely released. It's a GUI-driven software tool. It actually works reasonably well most of the time. It takes about 30 seconds to go from raw files to calibrated spectra. Essentially, if you look over here, you'll see the little images tab here. If you click on that, then you can upload into different folders your object files, your various calibration files, darks, biases, thorium argon, and so on. You can then step through the process, which is outlined under right here, either one step at a time, or if you're courageous, you can click run and have it try to do everything at once, which sometimes works. And then it produces output, which is single order spectra, and then a spectrum where it combines all the individual single order spectra into one spectrum. And you can see here that it's successfully done the calibration for the different orders, and you can see our short wavelength limit here is about 3916. So certainly short of 4,000 angstroms, although not perhaps quite as short as I'd like to get. There are some issues with it. Here you can see some outputs from individual orders. So spectra look reasonably nice. The error messages are pretty cryptic sometimes, actually all of the time, but perhaps those of us who are Python users will make it feel friendly to us. I don't know. It has some issues with multi-file reductions. You should be able to give it multiple targets, multiple spectra, and have it do all of them. It doesn't always work. As I said, I'd like to go a little bit shorter than order 57, so a little shorter than 3916. The light is there, the order is there, the software, we're really pushing its designed to get down there, so that's really the issue we need to work with. Continuum fitting is a little bit hit or miss, and then if continuum fitting doesn't work very well, then the order combination process certainly doesn't work very well either. Those are probably the two most significant problems at the moment. The first three, I think, are easily fixable, and we are a beta test site with Shelyak to try to address these issues, and they're pretty responsive. And lately they've been more responsive than I've been because I've been busy with other things. So I see this happening sort of over the next couple of months, getting these things fixed. So some single order spectra for a few A stars, just to show off some spectra. This one is, so it's Delta Aquarii, Nu Sig, and Rho Aquilii, and those are chosen because they roughly span steps of about a magnitude. So Delta Aquarii is 3.3, Nu Sig is about 4, Rho Aquilii is about 5. The exposure times here are 480 seconds for Delta Aquarii and 900 seconds for the other two. And this one is centered around H alpha. H beta is, I have not formally measured throughput for this, but the throughput seems to be best around 4,800 or 5,000 angstroms. So there's H beta, and then H gamma. We're starting to get somewhat noisier, but still, we certainly have signal down there. So trying to sort of summarize what performance is like, so that the plot on the right shows what the signal to noise is like approximately in this spectra that I showed you for a third, fourth, and fifth magnitude A star in 900 seconds. And the limitation is primarily, telescope pointing and field of view. You have to be able to find the target and guide on it. And the CCDs and dark noise in the CCD. My estimate would be that you can go down at 500 nanometers to 8 or 9 in V, obviously depending on the color of the target, for a signal noise of 20 or so. So it is a bright star instrument, but that's not a big surprise on a 0.5 meter telescope. Showing off a more interesting star to me, since I'm a cool star person, here's 1200 seconds on AR-LAC, which is an RS-CAN-VEN, again at H alpha and H beta, and there's some cosmic ray and other issues here, and around the H and K lines, which is pretty noisy here, but certainly the reversals are definitely visible. So I think this at this point represents kind of a lower limit of what we should be able to do when everything is working smoothly. So where do we go from here? I think we're working on some improvements to how we guide and how we set up to make the process more user-friendly. Bill's done really nice work at drafting an operating manual. So we'll get that finished so it's available for people. So using it should be a fairly transparent procedure, particularly for people who are familiar already with ArcSat, but even those who aren't. There's an incomplete manual for the software at the moment, and I'm adding to it and rewriting it to make it specific to our application. And I think reasonably we can anticipate availability for users before the end of the calendar year. People could use it now, but recognize that there's some shared risk involved. We had hoped to have this ready last year, but COVID makes things a lot more difficult than any of us had ever planned. But I think this will be available, and it will be an added capability for the 0.5 meter for bright targets. All right, so that's it, and I'm happy to take questions, and I may punt some of those questions to Bill, depending.
Thank you, Derek. It's a really nice talk of a really neat capability add-on, I think, for ArcSat. So I'm eager to use it myself. Let me just check and see if there's any questions on the chat before I go to the ones that I had written down. Nancy had a question, so let's start there.
Sure, thanks. Thanks, Derek, for that summary. It's really nice to see the progress. So I know that there's been a very few so far attempts with coordinated observations with the Shelyak and the Eshell on the 3.5 meter, I think primarily for sort of testing things out. And I guess I'm curious whether, you've thought about, how to, I'm sure there's a need for more, and that's fine. I'm not questioning that. I guess I'm curious as to whether, what other types of synergies you could envision between this instrument and the complement on the 3.5 meter.
Well, I think one is if people are using, say, the diffuser, for example, they're going to be looking at relatively bright targets with a 3.5 meter. So this might be something that you could use at the same time if you wanted to monitor, for example, stellar activity levels in H and K or any of the Balmer lines for targets that you're looking at exoplanets with. So that might be a use for it as well. So that kind of thing, I think, is a good synergy. Other than that, I think, it depends. I think it's probably more likely to be synergistic maybe with instruments down the road that are really higher resolution. So, we're talking about a next generation spectrograph on the 3.5 meter that's sort of 100,000 plus resolution. And then this becomes a good complement at the low resolution end.
Thank you.
you might also think of adding extra time cadence as well to some of the longer duration monitoring programs. Brett Morris talked about a long-term calcium H&K monitoring program, activity cycles over many years. This could provide higher sampling without using the 3.5 meter.
That's true. You could certainly fill in the gaps, especially with some of the brighter targets, and particularly with some overlap, so that you observe at the same time. So for calibration purposes.
I had 2 technical questions while we wait for other questions. First is, can you comment on what the readout times were? And then if you could also output the raw FITS files to not go through the auto reduction.
Oh, absolutely. It's not auto reduction. It's after the fact reduction. So you certainly get the raw FITS files. The readout time, I don't think I've actually measured it, but it's seconds. It's not very long.
10 to 15 seconds.
Yeah, something like that.
Not like the shell on
No, definitely not.
Other questions? As you think of them today and tomorrow, I encourage you to post them on the Slack channel for instrumentation, which has been pretty busy. And I think I'll hand it back over otherwise to Nancy for any final comments.
Okay, thanks.